So I think that we have from the Kepler mission we certainly have some data from the first 42 days of operation at a point that ended last year at about this summer. So they are required to report their data within 1 year after they acquire it. And so in the middle of June, they reported what they had done in the spring and early summer of last year. And that amounted to 42 days worth of data. So I'd like to talk about 42 days worth of data from Kepler, and this is supposed to be a 3 or 4 or 5 year mission to search for Earth-like planets. And it has to be that long because if you want to see an Earth-like planet in an Earth-like orbit, you want to see it at least 3 times to be sure of what you're doing, and so you need at least 3 years to do that project. So from this data, I've selected a subset of the 400 candidates that were published. And I will just assume that these data represent planets and that I'm not going to worry about false positives in here. It may be that there are some in there, but let's just assume that they're complete, that they're correct. And then I took the subset of that was complete in the period range that they claimed. They wanted to see at least 2 transits of an object, and so it had to be at least 20 days, and they said, well, it's really 17 days. So I picked 2 to 17. There's a reason for doing all of this. Hang on. I picked 2 to 17 days as the complete sample, so you're not missing anything in that period range. Okay, that's the point. And then I looked to see what Jupiters they had, and I'll show you a graph of it. Well, here, I'll show you the graph. No, this is the graph, and it shows, this is plotting radius on the bottom axis of the planet. So big planets are on the right and little planets are on the left, and Jupiters are on this range and Earths are over here, and Uranus and Neptune are in the middle. And this is the number of planets in each one of these 1 Earth bins. So in that 9 to 10 Earth radius bin, which describes Jupiters pretty well, there's that many of them, whatever this is here, a few, 5 or so. And each bin so on down here. So this is the data plot, and so I'm just going to focus on this part here for the moment, which is the number of Jupiters. So let me go back up. So thinking about that and asking the question, is that number that are seen there, which are pretty small, there are only 5 in each bin, but they're good numbers. Does that agree with what we would have expected? And you can go through a calculation and use some data that was obtained a couple of years ago that was also complete in the sense of being complete in that mass range of Jupiters and all the way down to 2 days. So it was in the range of 2 days to 2,000 days. So using the formula for that was derived from that data, I just looked at the 2 to 17 day range and said, how many should Kepler have been able to see in that range? And it turns out that number to within the error bars is identically equal to the number that was actually seen, which is sort of fortuitous, and the number is about 30. So if you add up all those little bumps there's about 30 of those Jupiter-sized planets. And I thought, this is fantastic, this is good. That means that the first study was really right, and furthermore that the Kepler guys are doing it right, and probably that they're not messing up too badly, at least in the Jupiter size range for signals there. So that's a good thing. So now you can jump from that to, and you saw the graph. Let me go forward. We'll skip this one that just shows the region that, some work I had to do in the middle. All right, so this is the data that I extracted from the report. Now you'll see the way I plotted it here, it goes down to smaller and smaller things, down to about 1 or 2 Earth radii. This is the Earth range. And the graph marches up here. So just to show what I did, I took these data points here that went up, and on this particular piece of log paper, they form a nice straight line. And so, the scientist in you says, fine, you get the ruler out of your desk drawer, you draw a line. And that's what I did. And I noticed at this point it was going to fall off a little bit, but that didn't worry me too much because this is down at the bitter end where you're looking at small radii, and they're not really sure that they're complete there. And in fact, they stop below this point in this particular publication. But technically, the study Kepler will go down to 1 Earth radius, so it will include this area up here, the target range. But this is what we've got so far, which is basically the ice giant range. Jupiters that are getting less and less massive, smaller and smaller in diameter. And now the question is, since this fits such a straight line so beautifully here, I'm sure that the next data that comes out won't be this lucky, but now you have a choice. You can either extrapolate this and say, okay, fine, the number of Earths that we're going to see is way up here, like 2 orders of magnitude in addition to the number of Jupiters that we're seeing down here in these hot periods, these short periods, these very short periods. These are planets that are really close to their star. These are not habitable planets, but we're counting rocks right now, so let's stay with me for a minute. So we can either extrapolate up there and just make a prediction, or we can say, oh, hey, this point here is really right, and it's really turning over, and it's down here somewhere, and this is the way nature is really going to turn out, that it stops going up this ramp. So you get your choice, but I think that somewhere in this range between here and here, which is almost less than a factor of 10, is pretty good prediction from 42 days worth of data. So I carried on with that, and I can't remember what's on the next slide. Ah, yes, okay, fine. So this is a continuation of the first slide. So like I said, I fit this ice giant trend. I assumed that this smallest radius bin was not complete because they're down in the noise at this point, and there's a good reason for not including all of that data. And then I extended it to 1 Earth, up to that green area, and you can count the numbers that you get there. Now you have to turn around and say, well, these are hot Earths. I don't really care about those, but they're telling us something about what's going on in these solar systems. And so now the good news part of this talk is in the last 3 lines here. So if you try and extrapolate this back to, these are planets that are really close to their star, and so you say, well, how many are there going to be out in the habitable zone, which is 1 AU from their star, these stars typically. Now you have to use a leap of faith or an equation or some extrapolation. But I use the same data for the Jupiters about the distributions with distance, and I'll apply that same idea for small planets. So there's an assumption there. So we can extrapolate back to the habitable zone region, which in my case is going to be from Venus to Mars, and also for the subset of planets that are between 1 and 2 Earth radii. And the reason we choose this is because 1 Earth radius is obviously what we're standing on, and 2 is about 10 times the mass of the Earth, and that's about the limit where people think that you can have a solid body without sucking up a whole lot of hydrogen and helium on top and turning into a gas giant. And then, so I got a number, I compared that to the sample size, and that ratio gives you n sub e in the Drake equation up here. It's actually, it's what people have, because people have not been paying that much attention to the Drake equation. Somehow, a few years ago, we ended up calling this eta sub Earth. So, but n sub e is better because it should be a subscript, because it's easier to find on your computer than an eta. And it's the same number, and I can't give you that number right now because I just haven't checked all of my math and everything, but the number comes out high, is what I can tell you. And otherwise I wouldn't be up here talking about this. It comes out high, and I think that this is a very positive thing for all of us. There may not be many dollar signs out there, but I think that there are a lot of rocky planets out there that we can expect to find around nearby stars. And by high, I mean lots. The solar system is high. It's got an n sub e of 2 or 3, depending upon how you look at it, which planets you're counting and when you're counting them. So high is somewhere up in that neighborhood, okay, and let's just leave it at that. And I think that that's a very encouraging thing, and for me, I am very happy to be able to bring that bit of positive news, I hope it works out in the long run, to this meeting, because I think it's one of the few bright spots that we can think about it today. Thank you.